Further applications of the derivative. Maxima and minima. You can think of an absolute maximum as the highest point on a graph, and the absolute minimum as the smallest. You can think of a local minimum as a minimum that occurs in a small area, and a local maximum be a maximum that occurs in a small area. So with those ideas in mind, if we look at our picture here, we have local minima at A, Q, and S. We have local maxima at P, R, and B. Our absolute or global minimum is at S. Our absolute or global maximum is at B. Now, on a closed interval, a continuous function will always have a maximum and a minimum. However, on an open interval, there is no such guarantee. The extreme value theorem tells us that if f is continuous on a closed interval AB, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d on the closed interval AB. Some terminology. Extrema can occur at stationary points, singular points, or endpoints. Stationary points are points where f prime of x is equal to 0. Singular points are points where f prime doesn't exist. And endpoints are the end of your closed interval. Singular points and stationary points are called critical values or critical points. Here we can see that we've got a relative minimum at the endpoint, the left endpoint, a relative max at a stationary point, a relative minimum at a singular value, another relative max at another stationary point, an absolute minimum at a third stationary point, and the absolute maximum at the endpoint of the interval. Fermat's theorem tells us that if f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c must equal 0. We can see that with our green values on the graph. If f has a local maximum or minimum at c, then c is a critical number of f. Now, to find the absolute maximum and minimum values of a continuous function f on a closed interval, find the values of f that are critical points on the open interval AB. Second, find the values of f at the endpoints of the interval. And third, the largest of these values from steps 1 and 2 is the absolute maximum value. The smallest is the absolute minimum value. As an example, let's find the extrema, the maximum and minima, for f of x equals x squared minus 4 over x squared plus 4 on the interval -5 to 3. Begin by computing the first derivative using the quotient rule. When we factor and simplify, we get f prime of x is equal to 2x times x squared plus 4 times x squared minus 4 divided by x squared plus 4 squared. F prime of x is equal to 0 where the numerator is equal to 0. These values occur at x equals 0, +2, and -2. There are no values where the derivative does not exist, since the denominator, x squared plus 4, is never equal to 0. And so we go ahead and we check our critical values, 0, ±2, and we check our endpoints. We find the function values at these points are at -5, we have 21 over 29. F of negative 2 is 0. F of 0 is negative 1. F of 2 is 0. And F of 3 is 5 over 13. So our maximum value occurs when x is equal to negative 5 and y is equal to 21 over 29. The minimum occurs at f of 0, which is negative 1. The first derivative test says suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then f is a local maximum at c. If f prime changes from negative to positive at c, then f is a local minimum at c. If f prime does not change sign at c, for example, if f prime is positive on both sides of c or negative on both sides of c, then f has no local maximum or minimum at c. For example, f of x equals 3x to the 4 minus 4x cubed. In this example, we differentiate to get 12x cubed minus 12x squared, or factored, we get 12x squared times x minus 1, and we set that equal to 0. This tells us that x is 0 or 1. If we look at values both a little bit larger and a little bit smaller than these critical points, and evaluate the derivative at those points, we can tell if those are indeed maximum or minimum values. So we see f prime of negative 10, a value smaller than 0, is less than 0. We look at f prime of 0.5, and that's also less than 0. Meaning 0, it's not a maximum or a minimum. We have, in fact, at x equals 0, a situation similar to figure D. Now, if we look at a value just a bit smaller than 1, for example, 0.5, and something larger than 1, for example, 10, we see that f prime of 0.5 is less than 0, and f prime of 10 is greater than 0, which means that we've got a minimum value at x equals 1, similar to figure B. Function itself looks like this diagram here. So at 0, we have no maximum or minimum, and at 1, we have a minimum. Gymnast Clothing manufactures expensive hockey jerseys for sale at college bookstores in runs of up to 500. In dollars, it costs C of x equals 2,000 plus 10x plus 0.2x squared, where x is the number of jerseys. How many jerseys should gymnasts produce per run to minimize the average cost? Let's begin by figuring out what the average cost is. C bar in this case is equal to 2,000 plus 10x plus 0.2x squared divided by x, or 2,000 over x plus 10 plus 0.2x. Differentiating, we get C bar prime equals negative 2,000 x to the negative 2 plus 0.2. Simplifying and setting that equal to 0, x is going to be plus or minus 100. We obviously know that we can't make negative 100 jerseys, so the minimum has to be at 0, 500, or 100, with 0 and 500 being the endpoints of the closed interval. If we evaluate C bar at 100, we get $50, which turns out to be the minimum. A graph of C of x shows that indeed 50 is the minimum. We can follow some steps to solve an optimization problem. The first thing we want to do is identify the unknowns and possibly use a diagram. These are typically the quantities asked for in the problem. We then want to identify the objective function. This is the quantity that you want to maximize or minimize. Name it explicitly. For example, let S be the surface area. Identify any constraints. These are equations or inequalities relating variables expressing limitations on the values of the variables. Then we want to state the optimization problem. This will have the form maximize or minimize the objective function subject to the constraints. We then want to eliminate extra variables. If the objective function depends on several variables, solve the constraint equation to express all variables in terms of one particular variable. Substitute these expressions into the objective function to rewrite it as a function of a single variable. In short, if there is only one constraint equation, solve the constraint for one of the unknowns and substitute into the objective. Also, substitute the expressions into any inequality constraints to help determine the domain of the objective function. Then find the absolute maximum or minimum of the objective function. We do this by differentiating and setting it equal to 0.